All right, the last video cut out before I finished going through multiple choice number 9, which is fine. I will start with multiple choice number 9. It's a continuation of the prompt that was used for multiple choice number 8. But whereas multiple choice number 8 was a thermochemistry question, multiple choice number 9 is a redox question, where we are asked in the fermentation reaction, ethanol is the product of what half reaction, and carbon dioxide is the product of what half reaction. In order to figure this out, I need to figure out whether or not the carbon, as it transitions from being part of the glucose molecule to part of the ethanol or carbon dioxide, is reduced or oxidized. And I'm going to find that out using oxidation numbers. So I'm going to go through each molecule in this reaction, and I'm going to assign it oxidation numbers. I'm going to start with oxygen. Oxygen, unless it's part of the oxygen molecule for just the oxygen element, in which case it would have an oxidation state of 0, or if it's part of a peroxide where it would have an oxidation state of -1, almost always has an oxidation state of -2. So I'm going to put a -2 above the oxygen here. And because I have 6 oxygens overall, that's an oxidation state of -12. Hydrogen, unless it's part of a hydride or the hydrogen element, has an oxidation state of +1. I've got 12 hydrogens, so that's an overall oxidation state of +12. This is a neutral molecule. There's no charge on any of the molecules in this reaction, so the oxidation numbers should all add up to 0. +12 and -12 already add up to 0, which means that the oxidation state of the carbon as part of glucose is 0. That's our starting oxidation state. I can take a look at the ethanols now. At ethanol, I'm going to start again with the oxygen. Oxygen has a -2 oxidation state. There's only one oxygen in it. Each hydrogen has a +1 oxidation state. So overall, I have 6 hydrogens. So that's a +6 oxidation state, but this is a neutral molecule. +6 -2 means that in order to make this a neutral molecule, the carbon altogether needs to have an oxidation state of -4. Which means each carbon has an oxidation state of -2. When we have transitioned from carbon inside the glucose molecule, sorry, that was meant to be the laser pointer, to carbon inside of the ethanol molecule, carbon gains 2 electrons. Because we go from an oxidation state of 0 to an oxidation state of -2, I'm going to say that each carbon gains 2 electrons, which means this is a reduction. Now let's look at carbon dioxide. If there's a reduction, this should be an oxidation. This is a redox equation now, so this should be an oxidation, but we'll check it with oxidation numbers. Again, we're going to start with our oxygen here. -2 per oxygen. I've got 2 oxygens, so it's -4 overall. It's a neutral molecule, which means that the carbon inside of carbon dioxide needs to have an oxidation state of +4. So it's gone from an oxidation state of 0 inside glucose to an oxidation state of +4 inside of carbon dioxide, which means it has gone, I'll just write this from here on the side, from 0 to +4. Each carbon, I mean, there's only one carbon in carbon dioxide, but the carbon in carbon dioxide loses 4 electrons, which means this is our oxidation. All right. I've already answered the question here. I did that on the last video, but it got cut off. The recording didn't quite finish. We will say that the ethanol is a product of a reduction half reaction because the carbon, when it goes from glucose to ethanol, goes from a state of 0 to -2. That's a reduction, gain 2 electrons. Whereas the carbon dioxide is a product of an oxidation half reaction because each carbon goes from a state of 0 to +4. They've lost 4 electrons. So D is our answer here. The next question is also an oxidation number question, or that's how I'm going to approach it. We have this box that has 4 different reaction equations, and then we are asked, of the equations above, the redox reactions are which ones? The way that we're going to figure this out is by assigning oxidation numbers, and if there is a change in oxidation state, from reactants to products, it is a redox reaction. So I'm going to go through each of these. Elements that are just pure elements have an oxidation state of 0. So the hydrogens and the chlorines that are part of the hydrogen and chlorine molecules each have an oxidation state of 0. In hydrogen chloride, however, because chlorine is more electronegative than hydrogen, it will have the electrons near it. It has an oxidation state of -1, whereas the hydrogen has an oxidation state of +1. So we have a change from 0 to +1 and 0 to -1. So this is a redox reaction. Our next reaction, sulfur trioxide reacting with water becomes sulfuric acid. Oxygens are going to have an oxidation state of -2. We've got 3 oxygens, overall -6. This is a neutral molecule, so that means the sulfur has to have an oxidation state of +6. Within the water, oxygen has an oxidation state of -2, and each hydrogen has an oxidation state of +1. Together, that's +2, neutral molecule. For the sulfuric acid, we're going to start with the oxygen. Each oxygen has an oxidation state of -2. There's 4 oxygens, so it's an overall -8. Each hydrogen has an oxidation state of +1. There's 2 hydrogens, so that's an overall +2. This is a neutral molecule, so these all have to add up to be 0. So we need a +6 for the sulfur in order for this to cancel out with the -8. None of these oxidation numbers change. The oxidation state of each atom is the same, so this is not a redox reaction. Reaction number 3. Hydrogen inside of this compound is going to have a +1 oxidation state. There's 3 hydrogens. This compound, it's ammonia. That's the compound. Overall, it's a +3 oxidation state. This is a neutral compound, which means the nitrogen needs to have a -3 oxidation state. Then we'll look at our water molecule here. Same as above, the water molecule, the oxygen's at -2, the hydrogen's at +1. In this ammonium ion, the hydrogens all have a +1. There's 4 of them, so overall it's a +4. This is not a neutral molecule. This is a charged ion, which means all of the oxidation numbers have to add to become +1. We have a +4 overall from the hydrogens, which means that the nitrogen is -3. And then in this hydroxide, the hydrogen's +1, the oxygen's -2. These add to get -1. None of the atoms here change oxidation state. So this is also not a redox reaction. Number 4, the ammonia, same as the reaction number 3. The nitrogen has a -3 oxidation state. The hydrogens all have a +1. Elemental oxygen has an oxidation state of 0. Then we get to this nitrogen dioxide gas. In the nitrogen dioxide gas, we're going to start with the oxygen, which has a -2 oxidation state per oxygen. We have 2 oxygens, so that's a -4 overall. This is a neutral molecule, so this nitrogen has to have a +4 oxidation state. We've gone from -3 to +4, so this must be a redox reaction. You'll also see that the oxygens changed from 0 to -2, just like it is inside of this water molecule as well, where the oxygen has a -2 oxidation state. So the oxygen here is being reduced, and the nitrogen is being oxidized. This is a redox reaction. So the answer here is B. Reactions 1 and 4 only are the redox reactions because the oxidation state of some of the atoms changes. The oxidation state of all of the atoms doesn't need to change. The hydrogen is +1 on either side of the reaction in reaction number 4, but there is an oxidizing agent and there is a reducing agent. There is a change. Some groups of bacteria use hydrogen sulfide gas, H2S, for chemosynthesis instead of water used in photosynthesis. This chemosynthesis process can be represented by the following equation. 6 carbon dioxides plus 12 hydrogen sulfides becomes glucose plus water plus 12 sulfurs. During the reaction represented by the equation above, the hydrogen sulfide is the what agent, and the sulfur undergoes what process? This is another oxidation number question. Let's assign some oxidation numbers. Again, I'm going to start with our oxygen. We've done carbon dioxide on a previous question, so I'm not going to explain it too much here. But the carbon here, because oxygen together has an oxidation state of -4, the two oxygens, each one's -2, and it's a neutral compound, the carbon has an oxidation state of +4. Glucose we also did in a previous question, we just did that in question number 9. Again, this is a neutral molecule, so because the oxygens and the hydrogens, their oxidation states cancel out, we got a +12 from all 12 hydrogens and a -12 from the 6 oxygens. The carbon here has an oxidation state of 0. So we can see that the carbon goes from +4 to 0. One of the main aims of photosynthesis is to reduce the carbon in carbon dioxide to turn it into this high energy molecule glucose. This is a similar process, it's just chemosynthesis. And so it makes sense that the carbon here is being reduced. The carbon goes from +4 to 0, which means carbon is reduced. It becomes more negative. The substance that is reduced is the oxidizing agent. Then we take a look at hydrogen sulfide gas. Our sulfur within hydrogen sulfide gas has a -2 oxidation state. It's going to elemental sulfur, which has a 0 oxidation state. So it's going from -2 to 0, which is becoming more positive. The sulfur is oxidized, going from -2 to 0, which means it's the reducing agent. During the reaction represented by the equation above, the hydrogen sulfide is what agent? Well, the hydrogen sulfide right here has the sulfur that is being oxidized, which makes it the reducing agent. Got that right here. And the sulfur undergoes an oxidation. The reducing agent is oxidized, which means A is our correct answer here. If you know that the reducing agent is oxidized and the oxidizing agent is reduced, then you can get rid of B and C because you know those don't match up with each other. So if you know your vocabulary for redox, that will help out. Here's an acronym that I use with my students. I say GERC OA, which means the gain of electrons, do a capital E, is reduction at the cathode. The substance, that's not how you spell substance, is the oxidizing agent. Gain of electrons is reduction at the cathode. The substance is the oxidizing agent. If you can remember these things, then you know that the reduction is the oxidizing agent. And then the other acronym is LIOA, where the loss of electrons is oxidation at the anode, and the substance is the reducing agent. So this was an oxidation reaction, which means that the substance that was oxidized is the reducing agent. Moving on to the next question. Several metals are used in the manufacture of permanent magnets. A student wanted to compare the relative strengths of some of these metals and their corresponding ions as oxidizing and reducing agents. He immersed a strip of each metal in an aqueous solution of a metallic ion and recorded the following observations. Cobalt and neodymium, the cobalt ion and neodymium react to form cobalt solid and neodymium 2+. Yttrium 3+ and neodymium have no evidence of reaction. Samarium 2+ and yttrium have no evidence of reaction. Here's our different chemical species. The oxidizing agents listed from strongest to weakest are numbered what? Well, here's how we're going to sort this out. We're going to sort this out by discovering which thing is the oxidizing agent. Now, if we look at the acronym that I put on the last page, the oxidizing agent is the one that is reduced, becoming more negative or less positive. In this first reaction, and this is the general case for most metal ions, it's the metal ion that is the oxidizing agent. So I'm going to highlight our oxidizing agent because the cobalt 2+ is the thing that is reduced to form cobalt. Even though the next reaction doesn't happen, the next two reactions don't happen, it is going to be the ions, the metal ions, these cations, that are going to be our oxidizing agents. Our reducing agents, which I'm going to highlight in red, are the solid metals. So our oxidizing agents are our metal ions. I'm going to write that one more time. The oxidizing agents, I'm just going to say OAs for brevity. OAs are the metal ions because they seek to gain electrons and be reduced. Now, this also uses our spontaneity rule. If there is a spontaneous reaction, then we know that the OA is above the RA in a redox table. So for our first reaction here, we know that cobalt 2+ is a stronger oxidizing agent than neodymium 2+, and neodymium is a stronger reducing agent than cobalt. If there's no evidence of reaction, this is non-spontaneous, that means that our oxidizing agent is below our reducing agent. We can actually create a table from this evidence. This is going to help us in question 12, so I'm just going to make the table here. But if you were looking at just question 5, you're asked about the oxidizing agents, so we're really only caring about numbers 5, 6, 7, and 8, because these are our oxidizing agents. But I'm going to build a table, a redox table here, and that will help us answer both of these questions. I'm going to start by writing out our half reactions, just our reduction half reactions. And I'm going to start with cobalt, because that's the reaction that we know is spontaneous here, where cobalt 2+ plus 2 electrons is going to form solid cobalt. And we know that this reaction on our redox table has to be above our neodymium half reaction, because this is a stronger oxidizing agent than neodymium, the neodymium ion. So I'm going to put the neodymium ion below. I can move these around on my page because I'm on a tablet, but I could have left some room in case I need to insert one of the half reactions in the middle there. Now I'm going to compare the other oxidizing agents to my neodymium and my cobalt. Neither of these are reacting with the cobalt here, so I have no way of looking at it. But I do know that yttrium is going to be below neodymium. Yttrium ion will be below neodymium because there's no reaction between this oxidizing agent and the reducing agent neodymium. The OA is under the RA. And if I'm looking here, I know that samarium has to be even below yttrium. That's going to be my order here. So yttrium 3+, and then my samarium 2+. This half reaction for yttrium would have 3 electrons for it to form a solid, and for samarium would have 2 electrons. And our corresponding reducing agent for each of these is the solid yttrium and the solid samarium. But here is our redox table, where this is our strongest oxidizing agent on the top, the cobalt-2 ion, and this is our weakest oxidizing agent on the bottom, our samarium-2 ion, which means that the strongest oxidizing agent from this list would be our cobalt, then our neodymium ion, then our yttrium ion, then our samarium ion. These are the oxidizing agents listed from strongest to weakest. This will also allow us to answer this next question, an equation that represents a non-spontaneous reaction. This word non-spontaneous means we're looking for an equation where our oxidizing agent is below our reducing agent. So I'm going to highlight all of our oxidizing agents that are in these questions. We have our yttrium, we have our neodymium, and we have our cobalt-2+. These are all starting with our oxidizing agents. Yttrium compared to the samarium reducing agent. We just built a table here. This oxidizing agent is above this reducing agent, so this would be spontaneous, so it's not A. Neodymium 2+ and yttrium. Well, the neodymium ion is above the yttrium, OA above the RA, so this would also be spontaneous. Neodymium ion and the cobalt, well, that's the reverse reaction of this spontaneous reaction. If the forward reaction is spontaneous, the reverse reaction is non-spontaneous. So you could have shortcutted this without building the table, but this helps explain the concept. The neodymium ion is below this reducing agent. So this is going to be our answer. That's non-spontaneous. But we'll check D just to be safe. Is the cobalt ion above the samarium solid? Here's our cobalt ion. Here's our solid samarium. Absolutely. So that would be a spontaneous reaction. I'm going to stop the video here, and I'm going to do these in shorter clips in case the feed gets cut off. And then on the next page, we're going to continue with more redox questions.